I'm going to talk now about electrochemical gradients, which are a very important concept when it comes to the physiology of all cells. People often associate electrochemical gradients just with nerve cells, but I'm going to explain that in fact electrochemical gradients are important for the functioning of any cell in the body, nerve cells representing a special case which can use the energy in these gradients to power action potentials. We'll come to that a little bit later. But to begin with, I'm going to start with a very hypothetical situation. I'm going to imagine that we have a container, and the container is divided into two parts, and there's a membrane in the middle of the container dividing two solutions. On the left-hand side, we'll have a concentrated solution of glucose. Let's say that it's 100 millimoles per litre glucose solution. On the right-hand side, let's have a more dilute glucose solution. It's 10 millimoles per litre. Now, the membrane down the middle is going to be permeable only to glucose. We're going to say that it's not permeable to water at all. So this is not an osmosis experiment. We're not interested in water moving across the membrane. We're only interested in the movement of glucose. And the question is, what's the glucose going to do? Now, clearly, there's a concentration gradient for glucose, which is going from left to right. And so glucose is going to tend to want to cross the membrane into the right-hand compartment, which has the dilute solution. Now this will carry on until eventually the concentration of glucose on both sides of the membrane is exactly equal. It's the same. Now that's not a very interesting situation, but I want to contrast that to what you would see in a very similar experiment if instead of glucose in the two compartments you had potassium chloride. So now on the left-hand side we've got 100 millimoles per litre of potassium chloride. And that means you've got potassium ions, which are positively charged, and chloride ions, which are anions, they're negatively charged. And they're all floating around in the solution. Now, in any solution of potassium chloride, you're going to have the same number of positive ions and negative ions. And so there's no charge imbalance, if you like. There's no extra positives, there's no extra negatives. It's a neutral solution, and it contains both types of ion. Now this is a relatively concentrated potassium chloride solution, and I'm going to say that this side of our little experimental cell, this is like the inside of a real cell, because the inside of a real cell has relatively concentrated potassium within it. Now the right-hand side of our little experimental cell is going to have a dilute potassium chloride solution, 10 millimoles per litre, we'll say, and also, to begin with, that has an equal number of positives and negatives, and so there's no charge imbalance. It's a neutral solution once again. There are just fewer potassiums and chlorides than there are on the left side. And this is going to be analogous to the extracellular fluid, which is more dilute in terms of potassium than what's inside a cell. Rather like with the glucose experiment, we've got a concentrated solution on the left and a more dilute solution on the right. But in this case, I'm going to say that the membrane separating the two sides is permeable only to potassium. Now that's going to be relatively similar to a real cell membrane, because as we'll see, real cell membranes are permeable mainly to potassium ions, more so than to some of the other ions that you might find in the cell. Now, the reason that a cell membrane might be permeable mainly to potassium ions is that it has a high proportion of potassium channels within the membrane. And those are going to be protein molecules which allow potassium through, but they don't allow anything else. So we have a situation now with a concentrated solution on the left-hand side, that's the interior of our cell, a more dilute solution on the right-hand side, that's the extracellular fluid, and a membrane separating the two, which rather like a real cell membrane, is mainly permeable to potassium ions. In this case, we'll say only permeable to potassium ions. What's going to happen? Well, we have a concentration gradient for potassium and for chloride, but chloride can't cross the membrane, so it's stuck where it is. Potassium can cross the membrane, and because there's a concentration gradient from left to right, some potassium will move into the right-hand compartment. So the concentration gradient drives potassium into the right-hand side. But this is where we have a situation different from the one that we saw with the glucose earlier, because potassium has a charge. It's a cation, it has a positive charge. And so for every potassium that moves across the membrane without chloride following, because it can't, we have an extra positive charge on the right-hand side, which we didn't have before. And of course, for every potassium moving through to the right, that's going to leave behind a negatively charged chloride on the left, which is now unpaired. So what's going to happen is that as more and more potassium crosses the membrane, the right-hand side becomes more positive, the left-hand side becomes more negative. And so we're creating an electrical gradient across the membrane. Now, if you're a potassium ion, you're now experiencing two forces. You have the concentration force from left to right, but you also now have an electrical force which is going from right to left, because you're a positively charged ion, and from the point of view of your charge, you would rather be on the left-hand side. So unlike for glucose, you now have two forces in opposite directions, a concentration force left to right, an electrical force right to left, and what's going to happen is that exactly the right number of potassium ions will move across the membrane, such that the developing electrical force will become equal and opposite to the concentration-based force, and at that point there'll be no more tendency for potassium to move. You then have an equilibrium situation. The forces are equal and opposite, and at that point there's no more net movement of potassium ions. So what we have at this point is a situation where potassium can still move to the right, or it can move to the left, but there's no more net tendency for it to move. Potassium is at equilibrium, but at that equilibrium position we have a membrane which now has a potential difference across it, an electrical difference across it. Inside, the inside of the cell is negative, outside, the extracellular fluid is positive. So in principle, we could put a voltmeter across the membrane, we could measure that potential difference, and that would be a voltage. Now, you could calculate the value of that voltage if you wanted to. There's an equation which would allow you to do it, but we won't go into that at the moment. It's sufficient to say that if you have a membrane permeable only to potassium, and you have two different concentrations of potassium on one side and the other, potassium will move until there's a voltage across the membrane. That voltage technically is called the equilibrium potential for potassium. Now that, in fact, is very similar to what we would find if we looked at a real cell, because, as I mentioned earlier, a real cell has relatively concentrated potassium inside, relatively dilute outside, and the membrane is permeable to potassium ions. So some potassium would leave the cell across the membrane, bringing a positive charge with it, and that would leave the membrane with an electrical potential difference across it. Now, in the case of a real cell, that potential difference is called the resting membrane potential of the cell. And in a real nerve cell, the resting membrane potential takes a value of minus 70 millivolts. It's always presented as the inside relative to the outside. So minus 70 because the interior of the cell is more negative than the extracellular fluid on the outside. Now, it turns out that in a real cell, the situation is a bit more complicated than what I've just described. And that's because there are lots of ions which can cross the membrane, not just potassium. And notably, sodium complicates things because sodium can move across the membrane too. So in a real cell, the resting membrane potential is not exactly equal to the equilibrium potential for potassium, but it's very close. And if you can understand what potassium is doing, then you're pretty close to understanding what a real resting cell is doing and why we have a membrane potential across that membrane.